Good morning and welcome to you all. Thank you so much for joining us today. I'm giving you a welcome from the southwest of England, county of Devon. I point that out because I note from the attendees list that we've got quite a varied audience today, globally, and also an interesting mix of background in industry and discipline. So welcome to you all. I hope you gain something from this short talk today. So I'll start with purpose. I think the purpose is relatively obvious from the title, but I just want to be a little bit more clear about the purpose of what we're actually going to be talking about. We're talking about, of course, making a choice when we have the opportunity to purchase or to decide upon a pump for a particular job or duty. Okay, we don't need to go too much into detail about what a particular duty is because a lot of the principles of what we're going to talk about are the same. Equally, I'm going to be using the PCP or the progressive cavity pump as our guide type today. If we were to use every single pump type, of course, it would be far too complicated. But again, most of the principles are the same. The things that we're going to look for over and above price and delivery, which might shock some of you if some of you are in purchasing or close to purchasing. But you'll understand why as we work through this today, why we park that, if you like, and concentrate on some other things because we're going to be really zooming in on points about whole life cost and value. Okay. And so we'll focus on the progressive cavity pump. But as I mentioned, as we talk about data sheets and where to find this particular information, often it will be the same for other pump types. I believe very much in keeping things simple. Okay. So although I'm sure that many of the esteemed audience is very well educated and experienced, bear with me if you are, because we are going to make sure that this is open to everyone at all levels. So at certain times I will dumb things down a little bit, but I'm sure that won't hurt. It always works for us to have a refresher, doesn't it? So we're going to talk about the progressive cavity pump, and I'm going to start moving on now, providing my mouse allows me to. So a little bit about me. Forgive the slightly embarrassing photograph, but we all have to have these days, don't we? So I'm Martin. Okay, I'm at Atlantic Pumps, which is the company I am a member of as we speak. I'm head of development of the water end of the business. So we have two distinct parts of this business, one we call core, which services general industry, but in particular, the focus on mining and quarrying. And then we have our water element as well. Okay. We quite organically moved into the water business or supplying and supporting the water business over the last 2 years. So not too long, quite a rapid organic movement because a lot of the things that we get involved in, our products and our knowledge has began to find its way to be very useful in the water treatment industry, particularly on the waste side, where lots of abrasives and trash, so rag and grit, are starting to become a problem. They've always been there, but not as much as they are today. And so there was quite a natural transition into supporting a different industry from that point. My details are there. I've also put them in the chat. And if you want to scan the code at any time, that'll take you to the website where you can get further information on our business. And at the bottom, of course, there's also a link there if ever you want individual lunch and learns in your local offices. Okay, I have car will travel, as they say. All right, let's get into it. So which pump should I buy progressive cavity? It's important to point that out because we're going to be focusing on that particular pump type for this exercise. So we're going to go across the basic construction and function. Now, that's really important because as we work forward through these slides and we start talking about whole life costs, it's important that we understand how pumps fail or how they wear, okay? Because that has a net and a direct link to its consumption of parts and energy. Okay, so that's really important when we do that. So for those of you who aren't particularly familiar with that type of pump, you'll get a little bit of a learn in basic construction and function, which might be useful. You would probably have to do the same for most pump types, at least have a grounding understanding of how they operate and how they might wear or how they degrade over time, because all machines do. The more work they do, they will suffer slowly or sometimes quickly, because those do help you make these informed decisions that we're going to be talking about. Then we'll talk about what's most important for best whole life costs, because what we're doing, the purpose of this exercise is to pick the right machine for the job. It's a little bit like, we can use plenty of analogies like buying a car ourselves. Do we want the most efficient car, or do we want the car that can do the most things like go off-road or go fast or whatever? So it's really important that we understand where the costs are going to come from throughout the life cycle of the asset. Then we'll go through a very basic exercise just to remind ourselves of what to look for, and that'll be a bit of fun. Okay, and then we'll draw some conclusions. So let's talk about the basic construction of the pump, because as I said, this is important for in this particular case. Right, so we have in front of us a positive displacement type, a rotary type positive displacement pump. In this case, it's a progressive cavity. Common brands, we'll talk about a few more brands at the end, although most of this talk is going to be brand less. Okay, it is neutral, it is desanitized, if you like. It isn't really that important. Your brand is got a lot more to do with particular supply agreements you might have, or favorites you might have, or lots of different reasons. Okay, but we're really going to talk about the equipment, if you like, in its bare essence here. So on the left hand side we'll start. Okay, that's of course an electric motor, which you will find in most cases. That will be what will be powering this kind of machine, but you can use other devices. There are subsea variants of these pumps for pumping grout into the seabed, for example, and they might use a hydraulic motor, which is serviced and powered from the surface, the sea surface. But generally speaking, it's electric motor in the industries that I've noticed that most of you are representing today. Then we have the gearbox, okay, very important component within the pump, not usually manufactured by the pump company. It's normally a bought out item because there's a lot of variation with those gearboxes. They can have different ratios, different service factors, and so on. Okay, but the gearbox is very important because it's the main link between the main drive motor and the pump itself. Progressive cavity rotary PD pumps of this type, they will run at rotational speeds, so RPM, much lower than the motor itself. So even if you use variable speed drives and you bring it right down to the minimum, it may still not be slow enough. So we often have, or almost always have, a gearbox for reduction. But also the gearbox helps us with a little bit of physics as well. It gives us a little bit of extra torque, okay, providing it is selected correctly. And we need that extra torque boost for starting and running of this kind of pump, because it relies on an interference fit between the front end there, the rotor and the stator, in order to perform its function. And so that interference fit, of course, requires a drive that gives extra load. So I talk about dumbing things down. We're not spinning a fan here, okay? We're turning a rotating element within a pump with lots of friction, okay, lots of resistance, including the resistance from the pumping system itself, okay? So we need a little bit of extra, I call them beans, okay, to get the thing going and keep the thing running. As we go beyond that, we've got a set of bearings here, okay? Now, not all pumps of this type have that set of bearings there. In fact, these days it's rather rare to find them. The bearings are there to give additional support, of course, to the machine itself, to the axial support and radial support of the shafting itself. Okay, most modern variants will have what we call close coupled, so it will do away with that set of bearings, and the gearbox will couple directly to the rear, just to the east here, or to the right hand side of that inner bearing. Okay, and it will directly couple into the input shaft, and it will rely solely on the small bearing at the front of the gearbox here to stabilize the machine. It's okay for lighter duties, for general service, sludge transfer and things like that, slurry transfer. Okay, but when you start hitting the harder stuff, so you got more tougher operating conditions, excuse me, it's very wise to buy or to use a more robust piece of equipment which have its own integral bearing. So the reason I talk about that so much is because it won't always be there, right? Then we got some sort of seal. In this case, it's mechanical seal. It could be old style packing, gland packing, which is again quite rare these days because gland packing is designed to leak in order to operate, and we don't like a lot of leakage, do we? So in this particular case, we have a cartridge mechanical seal, which will be oil filled, which is equally as important because when a PD pump starts to operate, it generates a negative pressure here on its inlet. Okay, so therefore, if we're starting to create some sort of level of suction, there's a risk of drawing in air, and if we draw in air, then we're not pumping forward as much liquid because now we're multi-phasing. All right, so it's very important that mechanical seals are sound and of good quality in your PC type pump. Very common out there in the field for those of you that are used to dealing with things on the front line. If a pump often appears to be not performing, we assume that it's worn out, so we'll spend lots of money changing the front end here, when all along it could have been the seal that was beginning to fail and it's sucking in air, and it could be quite a lot of air. And so our flow meter is telling us the truth, but it's not actually because the pump is down on efficiency, volumetrically that is. It's actually because we're putting in lots of air. Sometimes it can be spotted because your flow meter is jumping around a little bit and it's not particularly stable because of the amount of air going through, but just point that out while we're here. Okay, then we've got the suction casing with the transmission shaft, sometimes called the coupling rod. You've got two new universal joints, one at either end. Now we're starting to, including the seal, moving towards the sacrificial parts when we think about whole life costs, what can wear and break in the future. So we've got two universal joints, and then we've all of that. We've got the rotor itself, which is part of the main pumping element, the rotary part. And then around that in blue, you've got the stationary or the stator. Okay, we'll talk a little bit more about those in detail in a moment. But I just want to come back to the area here, all right, between the rotor and stator and the drive. So we've got a concentric part of the machine here. So this is all held on the bearings through the seal. But the rotor, as it operates, will wobble up and down. So we have eccentric movement. So that's the reason we have some kind of transmission between the two, which is flexible. In this particular case, we're using a carbon universal joint, but you can also use pin type universal joints for lighter duty. And in some cases, you can use a flexible shaft, which is a long, thin whip type shaft between the two. It makes the pump a lot longer, but it relies on that torsion, on that whip, rather than actually having physical universal joints, okay? And then, of course, you've just got your main casing parts here, which will be flanged for the pump. So it's important to go through that, because as we move forward, then things begin to fall into place as we talk about how a pump might wear, and therefore, what risk it might place upon us as far as reliability are concerned, because that folds directly back into uptime and whole life costs as well. So the operating principle of a progressive cavity pump, you don't need to read all this because I'll do my best to bring it to your attention. So we have that rotor, okay, as I just discussed when we looked at the cross section, that's turning within the stator, generally speaking counterclockwise. So we draw in at one end, our liquid moves through the pump, it conveys through, it progresses through, hence progressive cavity, and comes out the other end effectively. Okay, so our rotor is usually made of a metal, not always, but most of the time. Okay, and if it's a particularly abrasive liquid, it may well have a hardened coating on it. And our stator is usually a steel can, although there are other variants, that are modern variants, which are easier to take apart. But bear in mind, there will always be pros and cons to that. You get more integrity and better service life from the old style solid stuff. But you get quicker maintenance and more access to the inside of the machine with some of the more modern quick strip and speedy strip variants. All right, but within that we have a molded elastomer or rubber type material. Okay, so we've got a single helix rotor, and it's put into a double helix stator, profile stator, so the geometries go together. Okay, and what you get is then you get these cavities which work all the way through the pump, which you saw in the previous diagram. We'll see more of in a moment. Okay, so as our rotor turns, our liquid is drawn by then the pressure, there's a pressure drop here, negative pressure. It gets drawn into the first cavity, and then it works into the next, into the next, into the next, and eventually comes out the other end. And because we have an interference fit between these two elements, as we push our liquid forward into our vessel, which is normally pipe work, okay, which is of course restricted, then we will begin to build pressure. And the curve, although it's a bit of a lie, so to speak, when we were to draw it for this kind of pump, the curve is actually a linear curve. It's a straight line, because the outputs, the volumetric output or the flow, okay, is directly proportional to the speed at which we turn that rotor. So if it's turning at 10 RPM, it might give you 1 meters cubed forward an hour. If we turn that, speed it up to 20 RPM, it might give you 20 meters cubed, and so on. Okay, so it gives you an idea, again, the relationship between speed and output of the pump. It's important we learn something quickly about the sealing line, okay, in this particular kind of pump. All right, the sealing line is what is the term that we use when we talk about the contact point. Excuse me, getting a little dry. The contact point between that rotor and stator, and here you can clearly see those cavities, by the way. It's a much better sort of cross-sectional drawing. Okay, and where I've marked these marks in yellow, that's the touch point. Okay, that's the high point of the sealing line. But it isn't just at these points. It also carries on all the way through in this helical motion, okay, on the top, okay, the high part of the rotor and stator all the way through. So it's a long, okay, helical sealing line. There's lots of it, okay, and it's that contact point is where the interference fit sits. All right, and it's that which needs to be in good shape, so a good, solid interference fit in order for the pump to function, because if it doesn't, we'll get slip, which we'll talk about in a couple of slides, okay? So remember that sealing line is not hugely important to when we get to making choices in pumps, but it is important to understanding how they wear and how they degrade. The second term to be familiar with, if you can, is clamp. Okay, clamp's the term we use for how much, okay, of that interference fit or squeeze, you could call it, okay, between the rotor and stator. So not only do we need to know, or we need to have an interference fit all the way through, connecting between these two working parts, but we also need to have a certain amount of clamp or squeeze between the two. So if we have plenty of it, then we can resist the liquid passing back through the pump, and that, of course, therefore generates forward movement of the fluid. If we begin to lose it, then we can get what we call slip, which we'll see on the next slide. We'll slip back through and we will lose a percentage over time, okay, of our efficiency of the pump. And eventually when that wear gets really heavy, we may not pump anything at all. So we've got sealing line, we've now got clamp. And to bring the two together with the third, we've then got slip. Slip is the term we give when the sealing line, okay, begins to degrade, the clamp begins to degrade along that sealing line, and we get slip. So slip effectively is our liquid, okay, slipping back between those two components as they turn, as one of them turns. Okay, and the direction, of course, is back to source. Now, that slip will happen, okay, it has a direct relationship to what pressure we've got, okay, what head we're developing, or what head might already be there, static, so static and dynamic. All right, but once that head is enough, or even if it is always remain the same, but our wear is sufficient to allow that to overcome, okay, our clamp along our sealing line will get slip. So a little bit of our liquid will drop back. So rather than getting 100% moving forward, we might get 90. And as the pump continues the wear, that will drop to 80, 70, and so on and so on, okay? So we will get a portion of what we're hoping to be moving forward with the pump slipping back through it. Okay, we do separate webinars, talks about going into the depths of that, why it happens, how it happens, okay, what types of liquids have different effects on of abrasion and so on. So if you want that, look out for that course. If you want to go down to those depths, it's very, very interesting and worth doing, but it's not for this particular one, all right? If the higher the viscosity, by the way, so the thicker, if we're talking about wastewater, the thicker the sludge, let's say, the slip will take longer to occur and be harder to occur, because if my product is thicker, of course, it has a tougher job getting back between the rotor and stator. So that's why this kind of pump is actually more efficient, okay, the more viscous the liquid is. All right, so that's those three things brought together. It's important, okay, it's a little bit of refresher for those technical among you, all right, but those that aren't, you've learned a little bit something about how this pump works, and it's very important, as I keep saying, because it's going to relate to how we decide which pump is best later. A little bit of an interesting one to see here. Here's just some real life photos, okay, of a rotor, all right, with its nice shiny surface material ground away by lovely grit and high abrasives. And also you can see inside that rubber stator, which has been halved in this case. You can see, again, you can the witness marks are there. I just wanted to give you a visual representation of that so you can get it into your mind's eye. And also down here, just showing you, I've used little red dots to indicate what might be grit or fine abrasives. They do tend, because of the function of the machine and the way it operates, to hang up exactly where you don't want them to, okay, along that sealing line. And as the pump turns, it will work its way in there, and it will begin to cause what you see at the top there, all right? So that's physically how that happens. And I think if you've not already got there by now, you might be a little bit ahead of me, and that is that what we're going to be looking to do, if we're picking the right pump for the job, we're going to look to minimize wear wherever possible, so that we don't have this effect or anywhere near this effect quite as rapidly as we would like. And then we can push the service life of the equipment out, meaning that we will get longer life from it, and we'll get better whole life costs overall, all right? Because as we'll talk about shortly, whole life costs has got a lot to do with the use of components, or the consumption of components in a machine, as much as anything else, like energy and capital. Okay, we refer to the effect, if you like, or we measure it when we design this kind of pump. And I've been, should have mentioned at the head, I've worked for two manufacturers of this kind of pump and been involved at technical level right into design. So I can tell you that we do consider this very much in pump development and sizing, okay? And we're always looking to keep that, what we call rubbing velocity inside the pump, okay, which is the effect between rotor and stator, okay, down to an absolute minimum. And we have to consider within that the abrasiveness of the liquid as well. And you'll see more about that later as well. So that should be very much considered. And if you get that wrong, that's when you're going to have a pump that doesn't last particularly long, and you're going to have higher whole life costs. So what really matters when we're reducing whole life costs? This is just, you know, there's no audio on here, so you don't need to shout out your answer, but you can scribble it down if you like, you know. So which has the most impact if we were looking at a 10-year life cycle, let's say, of the pump we just looked at? What's going to be a major factor? Is it going to be energy use? Is it going to be maintenance cost? Is it going to be the capital cost of the pump in at the beginning? Is it parts over time? Which order do we think it is? Now, it can vary depending on pump type. All right. So that's a statement I'm going to make, because the next slide, some of you may go, well, what about? Well, we know what about. But sticking with the topic in hand and sticking with the pump technology in hand, it actually looks a bit like this, which is why it's starting to fall into place, I'm sure, as to why we've started off in the way we have. It's parts cost mostly in this particular kind of pump. Okay, maintenance time, which interlinks with that, of course, then capital, and then energy in that particular order. And it's in that order because it just is. And how do I know that? Well, 30 years of working with these machines in the field, replacing many that weren't particularly efficient, sometimes with the same pump, but just selected differently, or maybe even another type. Okay, I can give you, some really firm assurance that this order is correct. One of those manufacturers for 5 or 6 years, I was head of the aftermarket side of the business, which means that I was responsible for all parts movement and service. And of course, you don't get any closer to it than that. And we would run studies even on the consumption by industry of rotors and stators, for example. And that way you could zero in on which pump selections were successful, which particular applications, so what liquids might be pumped at what pressures and temperatures and so on. You could start to generate a picture of what's tough and what's easy, if you like, for the pump. And because we're focusing pretty heavily today on wastewater, because the bulk of the, forgive if you're not in that industry, but say the principles apply, bulk of the audience is coming from that background. So yeah, so that's the order. So we need to keep that in mind, okay, when we're making our pump decisions. Okay, there's a lot of information you're going to get when you go out to market, all right, but you want to keep these things in mind, and I'll explain why. Okay, I'm going to give you a little bit of an example from history, touching on what I mentioned earlier on. But when I was once in a job where I was responsible for the complete, UK and Ireland-wide distribution and sales, if you like, of spare parts. The numbers you're about to see were taken from real data. Okay. So in 2022, we ran a study at one of the manufacturers where we looked at the number of spare parts kits, that's rotor stator and the pieces you need to fit it, okay, and or bare shaft pumps, okay, because sometimes people elect not to repair a pump, they buy a bare shaft pump and just swap that wet end or front end out, okay, consumed by water companies in the UK. Okay, and this was calculated by, as I said, one of the leading PCP manufacturers where I was at the time. Now, the 10 water companies we reviewed, so we looked at the consumption of these parts for 10 water companies, okay, the not so much necessarily the larger water company, but the company that was using or consuming, therefore spending the most amount of money, okay, conducted 542 refurbishments in that year. So they either bought a spares kit or they bought a bare shaft pump and they replaced it, okay? At an average cost, we're going to use GB pounds, okay, at £3,000. I've been very conservative with that number, by the way, and those that are used to buying these sorts of things will probably think, well, that looks a bit low. Well, I've just been conservative at this particular point because it could be a pump that's very, very small that would sit on your desk, or it could be one that you'd have to, I've been involved with these sort of pumps up to 11 meters long, 250 kilowatts. So you have to find a point, okay? But it probably is in reality 1.5 times that, but we're going with 3,000. So that means that's a total of £1.62 million spent in just 1 year with one supplier on these wear parts. And the moral of this will become more clearly as we work forwards, but we'll jump ahead a little bit now. If we can reduce the consumption, okay, of all of those spare parts or replacement pumps, okay, then not only are we extending or reducing the whole life costs of those individual pumps out there in the field, okay, but we're also sort of verifying our decision-making process. If we buy the right pump that doesn't go through that sort of amount of spare parts, okay, then we know that we're making more informed decisions. So you could argue that those 542 pumps, of those, maybe a third of them had come to some reasonable point in their wear life, and the maintenance intervention was timely. But probably, and again, I'm just speaking from experience, I'm using a little bit of guesswork here, but it's quite well informed. Probably about 2/3 of those were premature, right? So we're looking to avoid that by better decision making. So there are 3 progressive cavity pump OEMs, which are the major suppliers into the water industry across the UK. So if we take just those 3 and put it all together, Okay, and then think about the annual spend across all of those water companies. Again, £20 million a year is a conservative figure. Why is that number important? Because that is part of the whole life cost. Okay, generally that number is part of that. So all of the pumps within that number, okay, they all make up that £20 million. And that's £20 million, a conservative figure that we probably don't want to be spending if we can avoid it. And since 2022, prices on average have gone up by about 24%. So again, we're playing with very sort of low imaginary numbers here. And I like to say, one of my favorite sayings is, as a pump nerd, as I like to see myself, if you always do what you always did, you always get what you always got. For those of you outside the UK, you might not be familiar with that saying, but it's basically saying other versions of that is, do something 3 times the same and get the same result is madness, and so on and so forth. It's that same methodology. If you don't change something, nothing's going to improve. Okay. So that's just some interesting numbers to bring you to. There are some individual sites in the UK I'm aware of that are spending in the hundreds of thousands a year on these components, and you could, for a lot of that spend, you could work it back to not the correct selection in the first place. Interesting. Okay, let's move on. That was just a little bit of interesting stuff. So let's have a little bit of an exercise. You can scribble down your answer. You only need to write number one, number 2, and number 3. This is just fun. If you don't know the answer, you can't really be wrong in this, but I'm going to give you a duty. So we're going to be pumping 20 meters cubed an hour, okay? And our static head is 3.5 bar, okay? We're pumping 6% dry solids, thickened and blended sewage sludges. And the site is Palm Beach. We wish, don't we, eh? Palm Beach Sewage Treatment Works. Okay, what a nice lunch break that would be. So we'll pretend the prices are all the same. So with the best whole life costs in mind, which pump will you buy? Let's just do this for a bit of fun. Is it number 1? I'll read it out for you. 15 kilowatt pump. It's 2-stage. We'll pump our 20 meters cubed an hour. That's great. And it'll be running at 133 RPM. And excuse me, that's my phone, not me. It will have a stainless steel coated rotor fitted to it. So we're talking about materials now with an NBR, so basically a nitrile rubber stator. Cost £9,000. Would you buy pump 2? So 7.5 kilowatt, nice and small, much better on the energy use, you might think. That's also 2-stage, does the right flow. It performs that flow or delivers that flow at 299 RPM. What it will do, it's a much smaller pump. It's got an alloy coated rotor. And the same, it's got an NBR stator. Alloy coated means it's just, it's an alloy type material of various types. It depends on the manufacturer, but we'll just call it an alloy, all right? But it's got a coating on it, hard coating on it, same as the first. Or would you buy pump 3? Somewhere in the middle, 11 kilowatt motor, single stage pump, 20 meters cubed an hour, 212 RPM. It's got a steel rotor and an EPDM stator. They're all the same price, okay? They all can manage the flow rate we want, okay, at the pressure that we have in front of us. So pick a pump. Say, if you don't know, you can write down, I don't know. That's a perfectly valid answer as well, okay? But just for a bit of fun, have a little guess. From what we've already talked about, which do you think would be the right pump to have, keeping in mind the whole life costs? So over the next 10 years, which of those pumps is going to cost you the least? I'll give you a few more seconds on that to have a think. If you're going to try and trip me up, the delivery's the same. I know, sometimes you've got to work that out. Okay, you can have all those pumps tomorrow. Sir, as you would say, or madam. Okay, so you've scribbled it down. As I say, don't worry about it. There's going to be no test or anything like that, but it's just an interesting thing because it's important that we understand if our decision will change once we've learned a little bit more. Okay, I'm going to bring you into some guidance, which will be quite important for going forwards. Now, this is the WIMES guidance. So in the UK, there's water industry, mechanical and electrical specification. Okay, you might have, if you're from other industries, you might have an equivalent. If not, you could learn something from this. So in the WIMES guidance for progressive cavity pump, you can see that written on over there on the right-hand side. Okay, that was issued April 2025. I am lucky enough, I say that slightly sarcastically, to be one of the consultees to the Pump Centre in the UK for when we review the WIMES for progressive cavity and also get involved in the peristaltic one as well. So I can just let you know from the inside just how much work goes into these sorts of things. These numbers aren't arbitrary. They don't just get made up. They are based on, a lot of experience and feedback from the end users. And effectively what you're looking at is a table which helps you decide or helps you pick your progressive cavity pump in this case. All right, so it gives you, of course, on the left-hand side, some examples of the pumped medium. Most should be covered. If not, you can pick one pretty close. Then it gives you guidance to the maximum rotor speed, and I'll talk about shortly why that's important, okay? It also gives you guidance to the maximum pressure stage of that pump. Now, this particular thing and this particular thing may not relate to all pump types, all right? Makes that very, very clear, but it is equally very, very important. So, for example, you can read it yourself, okay, if we're just pumping polymer, which is nice and slippery and easy to pump, we're using a PC pump, we can run that pump up to 1,000 RPM. Okay, without any real concerns, because the liquid is quite viscous, it's very self-lubricating, and the pump will love it, really, okay? However, if we go at the opposite end, we're pumping a thickened sludge, okay, some way down the sludge treatment stream, all right, so thickened, so therefore we have concentrated the solids in it by use of a thickening machine of some sort, okay? By concentrating the solids, don't forget we're also concentrating the abrasive solids. So if we got, which is quite common in wastewater, a lot of grit or small stones, or sand or whatever, okay, that will be concentrated with the organic solid. So therefore, our quite abrasive liquid or sludge is now quite a lot more abrasive. So it starts to make sense that in that particular case, remember we talked earlier about that speed, that rubbing velocity, which also incorporates thought about the abrasiveness of the liquid. So let's bring this down to basics. If we're pumping a very, what we deem as a medium or highly abrasive liquid or sludge, we want to run our pump as slow as possible to reduce the rubbing velocity. So therefore our wear rate or our wear effect, okay, is as low or as good as it can be. That way we will get longer mean time between failure. We will get a much longer time of operation and uptime between maintenance. And so therefore, we should have a knock-on effect of lower costs, and also, more uptime, process should be more efficient, so on, so on, so on, okay? We are doing what the plant needs to be doing. So this guidance is in here to give us some help on that. So if we're buying a pump to pump thickened sludge, what we should be doing is using this as a guide. And we can go back and challenge our pump seller, our vendor, whether it's directly with the manufacturer or if it's with a reseller, okay, an agent, okay, we should go back and we should challenge that we are getting what we should be getting according to the particular standards that you should be working to. This is slightly more complicated, and again, the detail and understanding of this part of the maximum pressure stage would be more clear to those of you that have either been on or after you've been on the more in-depth how these type of pumps work and where webinar, which, as I say, you can go to our website and probably find either a recording of that or they always evolve. So if you get a chance to come on the next one, it's a good idea because, I learn as I go too. But what it's effectively saying is PC pumps come in various, what we call pressure stages. A single stage goes up to 6 bar. A 2-stage pump goes up to 12 bar. A 3-stage 18, usually in steps of 6, although not always, but don't get bogged down with that, okay? So that's generally what we mean by stage, okay? So if we have a 12 bar pump, which is 2-stage pump, we have quite a long rotor and stator. In fact, it's twice as long as the rotor and stator would be on a single stage. So in simple terms, if we've got a lot longer rotor and a lot longer stator, we've got a much longer sealing line. So we've got more material to wear away before we start to develop that slip, okay? So the guidance says to us, if it's really, really abrasive and you're starting to pump at slightly higher pressures, that combination's not good. So let's slow it right down and let's use a 12 bar pump, even if we're only pumping at, say, 2 bar. Okay, even if our dynamic head is only 2 bar, still use a 12 bar pump because we're going to get a much better performance. We're going to get a much slower wear rate of that pump. That pump's going to be much more suited to that tough application. So what we're doing really is stepping up. We're beefing the pump up, even on what might look like a light duty. Okay. So that's how we would read this and how we would cross-reference from our, our offers. If we've got our 3 quotes, which we'll talk about later in front of us, we've put aside price and delivery, and we're now checking the technical details to see if it actually is going to be the best pump for my job, if it's going to give me the best performance, do what I need it to do, and not be breaking down every 6 weeks. So if we take our example, and now you're going to start to think, did I get the answer right? Okay. Our 20 meters cubed at 3.5 bar pumping, thickened sludge at Palm Beach. Okay, according to that specification we've just addressed, Number one, it should be two-stage. Why? Because we're 3.5 bar, and this says 3 bar per pressure stage. So we're over that, okay? So that's telling us that we need to go up. We have a thickened blended sludge, so I've purposely made it a little bit more complicated by weaving two together there. But even if we find both of those on the chart, blended up to 8 and thickened, 150 RPM is our maximum guidance speed. So if we now go get some quotes and they're running at 487 RPM, we know that's probably not going to be my best choice. I don't care if it only costs you £2.50, all right, it's probably going to cost you that every hour. So that's our guidance, that's how it works. So if we bring this into our decision-making process from the example I gave you, which pump did you buy? If you picked pump 1, well done, you would have been right in this particular example. Now, all 3 pumps potentially would do the pumping. So the cynical of you might say, well, they'll all do it. Well, they will all do it. But remember, we're talking about which pump is best to buy for the longer term, okay? Which is the technically correct pump to buy, not just the one that will do it, okay? I can go out tomorrow and buy you a £500 Toyota Yaris, and I can drive it up mountains and eventually it's going to break. Or I can buy a proper 4x4, okay, and I'll probably get a lot more life out of it. Okay, bring into my terrible analogies again. So yeah, but also what was equally valid as an answer was I don't know yet. Okay, because you quite right, you will also have been right there, because unless you have the knowledge already that we've just covered, okay, you would have been saying to yourself, well, I don't know yet because I need to go and check. And I did check the standards. I need to go and check my system curves. I need to go and make sure that this pump is actually appropriate. A little bit of insider information here. You know, your pump suppliers don't always get it right. You know, they're not all pump experts, depending on who you're using. If you're buying from a reseller, your local favorite, you know, engineering company that sells just about anything, they're not experts. That's not being unkind to them. They're not. So you do need to make sure that it's probably your responsibility to drill down to make sure you do get the expert knowledge. Some resellers, and I mean this in the nicest possible way, they need the business, they want an order, they might offer you all 3 of those and say, you choose, okay? They just want an order. But if you are dealing with people who are a bit more nerdy, who really do want to offer you the right pump for the job, okay, then you probably will get most of this information up front anyway, and they'll be able to justify it. But many people also won't. So make sure you drill down, push back, ask them for more information, okay, to help you make this informed decision. So all the pump has got, you know, it seems to be the biggest and chunkiest and the most, maybe even the most expensive if prices weren't all the same. Over time, it probably will turn out to be the best buy, okay? So yeah, well done if you got pump 1, or if you put, I don't know. Don't worry if you got pump 2 or 3, because at the end of this session, you'll pick the right one. So I'm just playing with some bit of fun here, and I'm saying, so what are the real prices look like? So I've just thrown in the real prices, and would you still buy it? Okay, so the real prices for this pump is 17,000. It's a much bigger pump than this one, okay? It's more than twice the size. This one's somewhere in the middle, pump 3, okay? But why was that the correct one to buy? Okay, not just because, okay, of the speed and the pressure stage. So the two things that jumped out was this is 2-stage, which is correct, and it's under 150 RPM. Okay, it's the right pump. However, this one could have done it, but it's running too fast. Okay, it's too small. It's 299. Okay, so that would wear in all, you know, in if all things were equal, that will wear pretty quickly. Okay, and I don't know if you spotted the materials, because that was a bit of a trick when I slipped in there. Okay, Palm Beach, we're near the coast. It's not uncommon for works, treatment works, pumping stations near the coast to have a certain amount of salt water involved. Okay, so we've got a stainless steel plated rotor here. Okay, so we're going to have corrosion resistance. And I did that as a little bit of a sly one, but you know, it's important that you understand that, okay, it's not just the performance, the materials matter, okay? I could have this right pump, number 1, but if I put in a standard, just plain steel rotor in that, okay, it would still corrode very, very quickly, okay? Once the surface corrosion begins to take effect on the surface of that rotor, it becomes rough, pitted, abrasive, you know, it will then begin to wear itself away effectively. Okay, so again, it's a bigger picture than you think. I hope this has already happened. I hope this is expanding thinking as to, you know, as to all the different things you need to look at to make the right decision. Okay, so that's that. I hope you enjoyed it. I did point out that it's the most expensive and the biggest. I'm just hammering on that. That sometimes might be somebody turning the nose up and saying, no, I'm not buying that. Maybe I can't get 15 kilowatts to the point of pumping, but it might be worth it. It might be worth that extra spend, that extra design or whatever, to make sure you've got sufficient power to use the right pump. Okay. And I only compared it to, well, I'm going to be in a moment when we look at costs, compare it to pump 2, because pump 3 kind of just was written off straight away, okay, because it's not only is it only single stage or one stage, so it's not in line with the specifications, it also has a steel rotor, so that would have corroded, and it has an EDPM stator, all right, which, okay, this is me going a bit deep. They don't like natural fats and oils, and that will have it will chemically react, for want of a better phrase. Okay, so it really is the wrong pump. All right, so a little nudge, and I like using my nudges. Just because pump 1 has a larger motor, it doesn't always mean that it would use more energy than pump 3. Okay, I'm not going to go into the depths of that today, but any of you that are more on the electrical side, understand the power, okay, we'll get that, okay, without going into detail. But again, that's for another course. But it's absorbed power, okay, so it's the power the pump is actually using when it's doing its job. That is important. That's what you're paying for, okay, when you're operating the pump. But just because this has a 15 kilowatt motor and this has an 11 kilowatt motor, it doesn't mean that that's drawing 15 kilowatts and that's drawing 11. That's not how it works. You just got enough power to start and run the pump. Okay, that might only be working with 9 kilowatts for all we know. Okay, and this one could be 10. So it doesn't necessarily mean that. I'll show you an example of that perhaps in a moment. So if we take those two pumps, okay, the little one, the big one, I'm going to call them P1 and P2, and we lay that out in a whole life cost sort of way, okay? So we've got the capital costs being much higher, so the difference is £8,000. It's a lot more money to pay, isn't it? I've assumed that they cost about the same to install, okay, just for easy numbers. Set of wear parts, almost twice as much on our big pump. Ouch, okay, big difference. Starting not to look attractive, is it? This is where it hits home. Because we have a pump which is running way too fast with the wrong materials, blah, 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 okay? And this isn't just a guess figure, okay? This is based on experience. It might need to be repaired 20 times over the next 10 years, every 6 months, okay? Whereas our pump, which has got the correct materials, it's running at the right speed, okay? It's going to be reliable, only 3, okay? So when we start weaving in the cost of the spares and the maintenance labor, okay, and winding that all together, then we actually start seeing the smaller pump becoming more expensive over a period of time. Okay, that's what we mean by whole life cost is more than what you just get on your data sheet, okay, or even on your whole life cost sheet, which you might be sent. Whole life cost sheets are a guess at best. Any manufacturer should be open to you about that. All the tests are done on water on the test bench. You're pumping very abrasive, thick sludge. Okay, they're very different things. You'll get a very different response out of the equipment. Energy. Okay, yeah, a lot more energy being burned. Okay, well, I'm using 26 pence kilowatt hour. You can use what you like. Okay, the differential will be similar. All right, we're using more energy, costing more, £28,000. But when we bring it all together, my mouse should highlight it. In fact, over 10 years, the differential, okay, is for so nearly £50,000 cost over 10 years. So our big expensive pump is nearly £50,000 less to own or operate and use over a 10-year period. So it's not obvious, okay? It really comes down to these key elements here, okay? If it's not right for the job, okay, it will need a lot more maintenance and your time and downtime. So we haven't even covered that. And at the bottom half, you'll see that I've pointed it out. What is the price of that risk? Okay, fines, over pumping costs, tankering, and overtime. Okay, they're not even folded into that little simple table. Right, so this is why I'm drilling it down to you. It's very important to make sure you pick the right pump, and it's not always the smallest and cheapest. Okay, here's a real world example, which I threw in there because I thought you'd find this quite interesting. This is a case study I've just completed writing. It's not quite the same, I understand that, okay, but it does give you a real world example. So recently we have been working with a water company and we've changed, okay, a rotary load type PD pump, okay, to a peristaltic PD pump. And the numbers are quite interesting. Capital cost, yes, the peristaltic pump, they're a lower manufacturing run number, so they're hand built. There's more cost to them. Okay, so it's actually quite a lot more, £14,000. Okay, more to buy at Capital Point. Okay, than the rotary low was. Again, I've done a similar thing. I've made installation about the same to keep things in cool. Set of spare parts. There's not much in it. Okay, but the rotary low pump, was, and then this is from real data, this is actual history, was being repaired every couple of months. So in 10 years, that's 60 times. And each time we're spending money on this set of wear parts and the labor to go with it. Whereas after an 18-month runtime, which is a proof of concept test period, okay, the peristaltic only needed one in maintenance intervention. So we stretched that out in 18 months to 6 in 10 years, okay? And when we bring all those numbers together, okay, you can see straight away, okay, which we'll totalize in a moment, but straight away that just the amount of times one pump needs attention over the other, that dramatically changes which is best choice. Okay, incidentally, what was also quite interesting, and this was all officially verified, it was done with proper power data loggers and recorded. Okay, we put a power logger on both pumps, which run side by side for a period of 7 days, and we found that the one pump drew 7.4 kilowatts just to do the same thing, and the other pump just 5.6. So we've got a very, going back to my previous slide where, don't assume because they both have a 7.5 kilowatt motor, which they do in this case, that they're both using the same amount of power. They're not, absolutely not. The energy difference is, in fact, over 10 years is so about £1,400 every year more for the energy to run one over the other. And that's a simple function of just how they work. A rotary low pump has to turn 2 shafts off one drive, 2 lobes, okay, spinning with interference fit, with resistance, okay, in that casing. Whereas a peristaltic pump is simply turning, okay, this armature, okay, with 2 rollers, and it's just constantly turning and crushing a hose. And so there is going to be a difference in power needed. Okay, there's less work for the drive to do on the upper pump. So, it should be obvious. But when we bring all those figures together over 10 years, just swapping one single 7.5 kilowatt pump on a site in real world, and that's really important to point out. The whole life cost sheets might have said something very different, but then those are generated by the people trying to sell you a pump. £156,000 just by changing one 7.5 kilowatt pump. Okay, as projected figures. So full case study is available through me if you want it, please ask. But I think that was really important to show you that what we're going through, there are real life examples where records have been kept, okay, and power has been monitored and recorded. And you can see that really does make quite a difference. So how can we check suitability? When we get our quotations, we're going to pretend we're getting 3 quotes in for our project. It's just one pump in this particular case, although you may have multiple. We really must have the data sheets for the pump. Now, I'm not talking about just the data sheet that might come, what we call in here often the WIMES data sheet, the data sheet from the manufacturer, okay? That is your codec, that is your checking of what you've asked for against what they've offered, all right? That's what you've got to be checking. So I put here, no. If you don't get it, you should wrinkle your nose and furrow your brow and go back to say, I'm joking here, by the way, tongue in cheek. What kind of outfit are you? Why don't you give me a data sheet? I must have a data sheet. I must understand what I'm buying. Okay, it's the description of what you're going to be getting and what you're going to be living with for the next 10, 20 years. Okay, there are 3 main points to check. Okay, application data, that's your benchmark against what the pump is being sold to you to do, against what you want it to do. Duty data itself, okay, so that's checking what we've been through just now. Is it running, what speed is it running at, okay, at what pressure, and does it fit into standards, and does it fit into what you're looking for, and materials of construction. So we're just going to quickly go through what we would have done in our earlier exercise. So in front of you, okay, I'm conscious of time, this last bit won't take long, okay. If you've got questions, you can start either typing them in the chat or whatever, and I'll get back to you. If I don't get it in today, by the time this webinar ends, I will email you. So drop your email address in. So we've got 3 different data sheets here from 3 different manufacturers for progressive cavity pump. It doesn't matter whose is whose. You may have seen them before. You may recognize them. It's irrelevant, okay? But they're 3 different manufacturers. They're laid out slightly differently, okay? So you will have to work your way through it to find the particular data that you want, but it's all there and should always be there. So for example, I've highlighted the pump speed in these 3 examples, found in different places, okay, but they mean the same thing. So you've got actual performance data here telling you that this pump will do 53 meters cubed an hour at 76 RPM or 12 at 19. Great. This pump will do its 43 meters cubed an hour, which is on the upper part here, okay, at 253 RPM. And this pump over here, it's got 3 duty points, so it'll be a variable speed pump. So it's got min, max, and normal. It's just telling us that to do 30 meters cubed an hour at 3 bar. At normal, it would be 183 RPM. So if any of these pumps were for thickened sludge, none of them are, by the way, but it's just example, then I think we'd agree that only one of them would actually, from the first point of check, would be suitable. Okay. So anyway, just be prepared to, when you're three different manufacturers potentially, that you might find the information in different places, but it's usually, so you've got actual performance data, you've got performance data, operating parameters. Okay, it's just different use of the language, but it means the same thing. But you'll also find really important stuff like what the sludge is, what the liquid you're pumping is. Okay, if that's completely wrong, the data sheet might be wrong, the pump might be wrong. You might need to refer that back and challenge it, just get it checked. It could just be an error, but it's worth doing it. Tells you the solid size, whether they're soft or hard. It tells you the pressures. Okay, you can check those against what you know will be the real pressure. You got discharge pressure here, 6.3 bar. What if you know it to be 8? Okay, that should raise an alarm bell. Go back and say, okay, you put 6.3 on your data sheet, but this is actually 8. Do you need to change the spec? Do you need to change the pump, or is this still okay? Let them come back to you and give you that information. But this is how you're going to be looking. Okay, you're going to be using these data sheets to find your information. If we use one of those examples, okay, I just kind of did it so I can skip through this slide really, but I've said, we're going back to our 6% dry solids, okay, thickened sludge. Wime says it should be 150 RPM, okay, at our nominal pump flow, okay, it says 183, okay, so that pump is not the right pump for the job, okay. Yes, okay, if you're only doing 15 meters cubed an hour at its lower end, it's only 95. But we know that that's not what we're always going to be doing. We've got a variable, requirement here. So we need to make sure that the maximum speed of this pump, okay, so this speed here, this 259 should be 150 or less, and the other speed should be, related to that for the lower flows, okay. So that's just a quick, sanity check. Check the standards against what you're actually getting on your data sheet. And I don't need to go through this slide because I kind of covered it when I talked about rubbing velocity or VGM. Okay, that's what the basis of these things. And I wanted to show you two things on this slide. Number one, that it doesn't matter which set of standards you're looking at, particularly if it's WIMEs in this case. All right, it's the same clause. So you've got the progressive cavity WIMEs here and the rotary lobe, but it's in both cases 5.2.3. Okay, that's what you're looking for. That's going to give you the guidance on speed and pressure stage. One thing I will say, and this is for those of you just really for awareness, really, particularly if you're in the UK, particularly if you're in a design or buying position, the clause for rotary lobe is being challenged at the moment. I've actually made that challenge back to the pump centre to have that reviewed. I don't believe it's actually correct. One obvious way of showing you that is if we pick our thickened sludge again, no, let's not do that. Let's pick blended sludge here at 5%. My limit is 200 RPM. Both progressive cavity and rotary lobe pumps work in a very similar way. One just uses rotor and stator, one uses a pair of lobes. But rubbing velocity or rubbing is rubbing. It doesn't matter what. You rubbing a elastomer, a sort of rubber type material against steel. It's the same, okay? So the faster you run either of these pumps, the quicker they're going to wear. However, there's a discrepancy because if we go to 5% on the rotary lobe, it says we can go up to 400 RPM. 5% over here, it's 200 RPM. So, and it's not quite clear because it also gives you 5 here. This doesn't help the selector. This is just going to confuse people. We could drop to 250, but that would make it a much bigger pump, which means, blah, blah, blah. Okay. I'm just pointing it out that if you're in a position over the next couple of years for buying rotary lobe, please be aware of that. You might want to go at the lower end if you want good whole life costs. So in my silly little example there, where you've got 5% mentioned twice, go for the lower one. Okay, that's just my little nod to help you until this is in some way made to make a little bit more sense. Okay, data sheet example, I think we've covered this. All right, where to look, application data, actual performance data, you'll find it in different sections, okay, in the sheet, but always be aware of those parts you're looking for. Those are important. So if little example here, my sludge is known to contain both salt and ferric chloride. Okay, I've got to consider that in my pump build. The manufacturer should have already done, but your job to check it. We've got cast iron, nitrile rubber, and alloy steel. Okay, that pump may not be suitable because we've got cast iron casings, all right, and we've got ferric chloride. Okay, this little fella here will corrode this little fella here really quite quickly, and I've seen that happen quite dramatically. I've seen it literally dissolve from the inside out of a pump casing into the point where it's coming out the side. wasn't the best idea. Somebody injected ferric chloride directly into the side of a pump because they thought it would be great. It would mix it nicely, which is not a bad idea. But unfortunately, whenever the pump had stopped, but the dosing pump had not, it was just filling, okay, a cast iron pump with ferric chloride, which was just, you know, just eating the pump from the inside out. But just be aware of that. Okay, if you are dosing any kind of chemical into your liquid, you also need to consider that when you look at materials of construction. Okay, it's not just the main thing you're pumping, because even the slightest contamination of certain chemicals will have or may have a negative effect, okay, on your pump. And when we get it wrong, I think I've shown you stuff like this. It looks like this. Okay, that's just for information only. Okay, pump running too fast. Okay, it's got a chemical dosed into it, which is also corroding the material heavily. Okay, once the outer coating has been stripped off, the base material is affected by the chemical, and you'll get very rapid pump failure. Just a little nod of information. Don't forget when you do, okay, you are buying pumps, don't forget your pump protections, okay. I haven't gone into it in detail in here, but they are important, okay, especially if it's a positive displacement pump, which we've covered here. Dry run protection, okay, senses frictional heat and trips the pump out of the panel. So if you get no liquid and you allow these pumps we've talked about today to continue to spin, especially if they're running fast, okay, you're just going to get frictional heat between rotor and stator, and eventually the rubber will melt down and you'll completely trash the pump. So dry run protection will sense that increase in heat uses a thermistor sensor in the stator of the pump, and it should trip your pump out. Okay, so make sure you ask for that if you think that's a risk. Overpressure, self-explanatory, okay. PD pumps will continue to generate pressure until something gives, okay. Always have overpressure protection on a PD pump. Okay, on the discharge side in particular, make sure you trip your pump when it gets above any kind of safe level. That level is up to you. It might be, you know, it will be certainly be in relation to either the pump capability or the pipe work and associated equipment. Similar with under pressure, often these kind of pumps are used to do a suction lift, so suck from beneath them. Okay, if you get any kind of obstruction or the liquid gets particularly thick, the pump will struggle to do that, and it will then heavily cavitate. So again, if you can put a negative pressure sensor on the inside in a similar way, and when it hits a certain point, say minus 0.2 bar or whatever, trips the pump out, okay, and again, protects your assets. So just remember those. And, you know, I'll just be honest, why are so many misapplied? Okay, competition, sometimes in competitive situations, manufacturers will reduce their pump size in order to reduce their price, in order to win an order. Okay, it's that simple. Be bold about it, be honest about it. And so that's often how it can happen. Sometimes the buyer experience or competence of the buyer, and that might not be a purchasing person, it could be anybody, okay, might not have the knowledge you now have today, but they also may just opt for a smaller, cheaper pump because, you know, they haven't got the experience to know that that's going to cost more in the long run. And sometimes, probably the most common one, replacing like for like. Pump keeps dying, so we'll just buy another one like it, right, and put it in, even if it's a different color with a different label on it. Unless you go back to basics, start with the system dynamics and work it backwards and make sure you've got the right pump, you're just going to get the same problem again. Always doing what you always did. Be prepared to go beyond brands. So I've celebrated a few different brands or plenty of brands actually, of all the different types of progressive cavity pump here to give everybody a bit of a shout out. Okay, so if it's possible, use the markets to your advantage. Okay, if it's not, then be sure to put the right pressures on your supplier. So of course, what I mean by that is, in some cases, you will be limited by either a standard framework agreement or preference or something like that. Okay, and you don't have much wriggle room to go and, you know, make other comparisons. But if that's the case, then, you know, this is more important to you than ever because you want to be able to make sure that you're getting the best one. A nudge, AMP8 will place huge demands on pumps, already is. We're already seeing some contractors come to us and say, you know, the suppliers that they're directed to are overwhelmed or don't think they'll be able to deliver. And so, you know, you might have to prepare to go to do some deviations in order to meet the project targets. So just be aware of that. And I thought there's another slide, but there's not. Never mind. Okay. Finally, about tip pumps. I kind of touched on this at the beginning. I think it's right to show you this. Okay. We started in mining and quarrying. That's where we get our expertise in abrasive and difficult to pump applications. As I said earlier, I've only been with the company about a year and 2 months, but I migrated over from manufacturers which were heavily and deeply involved in the wastewater treatment business. And the idea was that I brought that experience with me. And a lot has changed, and that's why we've been quickly and organically moving into water, because you now have a lot of rag, a lot of grit, a lot of other problems, higher throughputs, and things are changing. You know, more demand on treatment works, whether they're clean or dirty, and so things have got to change. You've got to go out there, look at different things, look at different options, innovate, optioneer, whatever you want to call it. Okay, and so companies like ourselves are becoming more and more relevant. And we're based up in Chesterfield, although I'm down in, I was about to say sunny Devon, but it's raining quite a storm right now. We've got our usual tickets that you might expect of a competent supplier. And I'll round off. I say thanks for joining us. I haven't seen if there are any questions right now. I'll refer to those in a minute and get back to you in a later time because we've just run over. Okay, and so if you've already left, sorry I missed you, but you might have been due to another meeting. Please scan the little code there with your phone and give us a bit of feedback. If you felt this short course was terrible, please tell me, because I'm always going to look to improve it. If you feel I missed something, tell me. If you felt it was quite good, that'd be wonderful to hear as well. If you feel that many other people should have this sort of training, pass it on. Okay, takes just a minute. So I'm going to say thank you because we've already overrun, and as I'm going to just repeat, if you've got questions, my email address or my phone number are both in the chat, and also you can put other stuff in the chat right now and I will come back to you when I can. All right, so thank you for coming. I hope you enjoyed it. I hope you found it useful. And if you ever get stuck, make contact, okay? And, there's no obligation. We'll always just come along and give you some advice if you need it. And have a great rest of the week and a great weekend.